Yes, so this is the elect 241 referred practice practice coursework. So for this, I've done all four components: SPI, buffer, calc, and control. And let's get start with SPI. I'm going to give a very quick recap what I did in this. So let's start with the code. What I did is made a file called SPI Master, which was obviously given, and then I added all the codes reset as given in this. 1 second. Yeah. So it gave me the inputs and outputs, and I've put that all here. And yeah, right. And secondly, let's do this. Yeah, this is better. Not really, actually. I'm just gonna do this. All right. Now let's go into architecture. I've added signal called internal SPI clock. SCL is SPI clock. So yeah, that will help me drive clocks to the other generators, clock generators. And I've added a shift register, enable shift. I named it enable shift, and enable clock generator, reset clock generator, and disable SPI clock. And this done is from SPI FSM, the state I used the state here. Yeah, free state. Sorry. Yeah, sorry about that. A finite state, and I used it in here, and that's why it's here. And the next thing I'm going to show you is the architecture now. The signals are shown, and now what I did in SPI Master is basically just wrote the components of all three parts I've used individually. For example, I've used SPI clock generator, and I've defined it here. I used SPI FSM, and I've defined it here, and SPI shift register, I've defined it here, and the test bench is here. Alright, then I've just connected these here. So now let's go to SPI clock generator. 1 second. Yeah, so I've added libraries. I've found this library in the lecture slides, so that's fine. Reset, enable system clock, and SPI clock, and it is according to the datasheet given. The system clock should be 50 megahertz, and I've defined that below. And SPI clock should be 1 megahertz. Okay, so the architecture is pretty simple. I've added a counter of 4 bit. I've added a counter of 5 bit actually, and this is used. I've used counter here to generate 1 megahertz of SPI clock. So and it's done here. I'll tell that later. And I've used count done, that will tell me that will show if that's 1, that the clock, the SPI clock has generated 1 megahertz. And that's internal clock. I just named it like that. This is very simple, and I've named the process count done process, and I've added the statement which says that. So what this does is counts till 24. I've took it randomly, and if the count done is 1, if this happens, then the count done is 1. That means basically 1 megahertz has generated, and if that is not 24, then this is 0. That's what I did. And down here is the counter, right? So all it does is is generate is all it does is generate 50 megahertz, just like this was used to generate 1 megahertz. Yeah, and yeah, there are cases if reset is 1, then counter if counter is would be set to 0, and if rising edge of system clock is up, then and also if it gets enabled and the counter as well, that means that 1 megahertz is generated as well, then counter is again set to 0, otherwise counter is incremented, and below is the clock generator. So what this does is it toggles the clock signal every time the frequency of the SPI clock is 1. It generates 1 megahertz. That's what it does. And I'll explain this. If reset is 1, then internal SPI clock would be 0, which is SPI clock. I've just named it. I've described it above. And it means this. Right? And if rising edge of system clock, then and also the count done is 1, then internal SPI clock would not be internal SPI clock, which means that it won't be 0. So yeah, that's what this is. Just describe clock generators in one different file. That makes it easier. Now we'll go back to master. The next thing, and I've added that component here. The next thing I did was SPI FSM. Added a finite state here. So here basically I've used system clock, SPI clock, reset, start, chip select as it was given, and I've added some few. So no, I've not added that. I've written it as it was given. Enable the clock generator, reset clock generator, and done, which I said I will be using here. And so the shift bit, which is needed in here, shift register, and the clock generator is from here. So yeah. So the architecture, I've had a type state D, which describes the 3 types of state I'm using: idle state, capture bit, and state. I mean, idle is capture bit is when that's the capture bit, this is the middle state, and then that's the end state. So these are just three states I'm using. And then that's I've added signal, which will say state, next state, which what a bit counter, which will count from 16 bits, and reset bit counter, enable bit counter, done bit counter, which is pretty self-explanatory. And then this is done last clock, so that means when the last bit is captured, like we're gonna shift bits, right? So in the shift register, so that's the done last clock is used for the last we capture last bit, enable last bit, that's last done, and that's internal done. So it just tells me which it just tells me that internal done and last done are pretty similar. I've just added it so that there is clarity, because I'm using one of them in somewhere else as well. So this is so when internal done is done, this case is pretty simple. Internal done and not the last done. And so now I've added the process of SPI clock, which clocks the last clock process. I've named it that as well. So when the SPI clock goes to 0, last clock is 1, else is 0. I've added a bit counter, which will count the length, count the bits, and when it does, Sorry, this video got stopped. I'm using this new software it took me. It's not free apparently. Anyways, so the video, I'm gonna make it short because I can't record more than that. Alright, so I've added 10-bit counter, which is pretty very simple. If it's 15, the bit count is 15, then yes, I have counted it. If it's not, else it's 0. Then I've added a last run process, which tells the if rising edge, if system clock is in rising edge, internal done is same as last run. And I've added bit counter process of SPI clock, reset bit counter. So when reset bit counter is 1, bit, and when the reset bit counter is 1, then bit counter will tend to go to 0. Else if rising edge, then bit counter is 1, if the rising edge and also another bit counter is 1, then bit counter will increment. So assigning state is pretty simple. If reset is 1, then idle will be the state. If rising edge of the system clock, then the next state will be the state, which is the signal I've defined above. So now we'll go into assigning next state. So yeah, so initially the next state is idle. Okay, state when idle, if start is 1, then if the process started, then the next bit is capture bit, in which will capture will capture the bit, and if not, it's idle. And if it goes to capture bit and the done bit count is 1 and the done last clock is 1, then it will go to end state. If not, it will stay in capture bit. And in end state, if done last clock is 0, then it will go back to idle. Otherwise, it will stay in end state. When I've added this just in case if there's error. And now assigning process. So these are the initial condition which is given. There should be 0. Chip selection 1, and it's pretty self-explanatory. Yeah. So these are the cases. When the state is idle, chip select is 1. Reset bit count is 1. Reset clock generator is 1 as well, and disable SPI clock is 1. And as told in the sheet that where is it? Yeah, chip select is held high at rest, and the falling edge of chip select will start a conversion. So in idle state it's 1, and then when it starts capturing, chip select will go to 0, and everything else also starts working. And end state, it will show internal done because it has finished capturing bits. And when others, it's same as idle. And that's the FSM. Now the master, sorry about that. Now the third component I've used is SPI shift register. In order to shift the bit, I've used a different beat so that it's easy. So I've added I've added D in and D out here, and the board. The rest is easy. Yeah. So I've added a signal called data, the shifted data, register shifted data, which will capture which will shift 16 bit, and I've named it as D out. Sense data. So if I've named it as sense data, if rising edge of the clock, then D in is the data. I've made this to simplify my work. Obviously it's a long process I've used, but it works actually. So yeah, shift come back. So process data, register shifted data. Shifted data 15 down to 1. Register shifted data 14 down to 0. Shift left. So we capture. So it says like you have to do most significant bit first. So that's why I've made it 1, so that it captures the most significant bit first. That it shifts left. So it shifts left, and shifted at 0 is data. And shift register process clock reset. If reset is 1, register shifted data will set to 0. I'll say falling edge, and enable is 1 as well. Then shifted data is register shifted data. This was pretty simple. I could have done it, I prefer not to. Alright, and now the architecture of the main SPI master. Since MOSI is 0 is given, like MOSI is permanently held low, and SPI clock is set to 1, so the internal SPI clock will be enabled and it won't disable SPI clock. Yeah, so I've added clock generator from here, and I've just added and connected those just like connected wires, and I did that with again, and I've combined them with FSM, and just so I've simplified SPI master for myself, and this is the test bench for this. Right, so I've added a new library I found online from Material, which helps me to the random number. Let's me create a random number. Alright, so that's the entity architecture. I've added all the initial conditions given above. By above I mean here. And I've added component SPI master, everything in and out. I've started the architecture. So here's the procedure. Send SPI. So it's just very simple. It says start function data will start sending MISO and variable data. So now variable data vector 15 down to 0. I'll use that to split data bits into 4, since I've used it like shifted like 4 bits thing. And data vector here will be assigned to data, and start will be set to 1. Wait for 250 milliseconds. Then it will start the first value. It will send the first value. Then the start will be set to 0 for I 0 to 15 loop. I've used 15 random 15 number. Then MISO will be data vector 15 minus I. Wait for 1 microsecond every time if I do this. And I've started the process, the architecture. I've named it tube, SPI master, reset to reset, easy stuff. Clock process. I've made the clock the system clock. I've enabled the system clock by doing this. Now test process, the process for the main test bench. Yeah, so the library I use, Material, will help me create random data. So variable data, I've used integer data for integer, random for random real value, seed1 for positive random real value, and seed2 for positive random real value. Alright, so we initially will wait for 10 nanoseconds, and then to reset, it will reset. Reset will be set to 0. Wait for that time, and yeah, for 0 to I only have 1 minute left. Alright, for I in 0 to 1 loop, uniform sequence to random, data will be integer flow random. I use this max. This is the max value I use, and if it will help me create random number with respect to this, and SPI send SPI start reset data. I've started all the segments, and this will assert this will check that if Y is data. If not, it will report mismatch SPI and CBRD. It will fail. Wait for 500 nanoseconds and end the loop. The board test pass. I've just added this just so that I can check it. It's right here, and this is used to finish the test bench. That's my test bench. So sorry for making this video long, but I'm just gonna test the test bench now. So for that, I'm just gonna simulate all of these. First I'll recompile them, and now I'll just come and simulate the test bench. Right. I'm gonna add this wave, and I'm just gonna run it. Alright, so this is the signal. Okay, I'm just gonna zoom out. As you can see, system clock is periodic, it has a purple wave, and as it was asked for us to do. So until chip select is 1 at the start, and until it goes down, the process won't stop, which is here, which shows. And once that starts, you can see that mostly it's always held low. We can see it's always 0 throughout this thing. And sorry about that. Right. And so the clock is held low at rest. So it's held low at rest. When it starts from the next rising edge, it will convert and it will be constant. Right. The system clock is zoomed in so you can see, and it also displays 16-bit value, and every time it shifts 1, so it shows everything needs to be shown for SPI Master. And that's my SPI Master. Next video will be for buffer.